We'll flip the question from which model to which constraint unlock. That reframe alone can slash indecision time. Welcome to AI on AI, where we unpack the machinery behind breakthroughs with both executive clarity and engineering grit. Today we're diving into tiny recursive models, or TRMs, a less is more approach that's beating large language models on hard puzzles like Sudoku, Maze, and RCAGI with only 7 million parameters.
Thanks for having me. If HRM was the first compelling argument that small networks can reason via deep supervision and multi-frequency recursion, TRM is the austere sequel that removes the biological mystique, skips the fixed-point math crutches, and simply backprops through a full recursion cycle to get both higher accuracy and better generalization.
And from the systems side, this is a compute reallocation story. TRM trades width for steps. Fewer layers, tiny parameter count, more iterative refinement, and it ditches the second forward pass for 8 during training, which directly halves one of HRM's hidden costs.
Let me put a business lens on that. If you can reach 45% on ArcAGI1 and 8% on ArcAGI2, with less than 0.01% of the parameters of the frontier LLMs, you're suddenly talking about deploying reasoning systems on edge devices in regulated environments with radically better cost-to-quality ratios and reduced data requirements.
The headline is nice, but the mechanics matter. TRM keeps two state variables, y as the current solution and z as the latent reasoning. It recursively updates z conditioned on x and y, then refines y conditioned on z and y, which is a clean reason-then-answer loop that's both interpretable and stable when paired with deep supervision.
The subtlety here is that HRM leaned on the implicit function theorem and a one-step gradient approximation, presuming convergence to a fixed point, which is tenuous when residuals are still large. TRM sidesteps the whole debate by defining a full recursion block and backpropagating through it. No fixed point assumptions, no brittle IFT proxy.
Let's rewind briefly. What did HRM get right, and where did TRM cut the fat?
HRM got two big things right: deep supervision over multiple improvement steps, and the idea that recursive reasoning can compress effective depth without BPTT over hundreds of layers. Where it struggled was the two-network hierarchy with loosely biological justifications and the extra forward pass for its halting Q-learning.
Exactly. HRM's pipeline did 6 function evaluations per forward, tracked gradients for the last 2, and added an extra forward pass to learn when to halt. TRM compresses this to a single tiny network, a single forward for halting, and full recursion gradient tracking for the final block, which is both simpler and empirically stronger.
Strategically, simpler is a feature, not a bug. Maintainability, auditability, and talent scaling all improve when your core loop can be explained on a whiteboard in 5 minutes.
Plus, the ablations showed that more layers harmed generalization on small data, while 2 layers paired with more recursion improved it. So the optimal point, counterintuitively, is a tiny 2-layer network taking many small steps, not a deeper network taking fewer big ones.
There's a principle from statistical learning theory peeking through. Think minimum description length. A shorter program that iteratively refines a solution may generalize better than a larger monolith that memorizes. Recursion is essentially an algorithmic prior.
Deep Dive 1. Walk us through the TRM training loop and why it's stable.
Sure, initialize y and z. For t-1 recursion cycles, update z with net xyz n times, then update y with net yz, but do this under no grad to warm up the state. Do one final recursion cycle with gradients, compute cross-entropy on the output head y, add a simple halting BCE on whether y equals the ground truth, detach states, repeat for up to n supervision steps with early stopping if the halting head fires.
The stability comes from 2 places. First, deep supervision acts like residual connections across time, preventing long-horizon credit assignment collapse. Second, the EMA of weights damps oscillations, which in these small data regimes is crucial to avoid divergence after early overfitting signals.
And you avoid the gradient mismatch pathology of one-step approximations because you're differentiating through the full recursion block you actually executed, keeping the learning signal aligned with the inference dynamics.
Importantly, the model learns to use Z as a chain of thought scratchpad and Y as the concrete proposal. If you omit Y from the inputs, Z is forced to carry the solution, which harms reasoning capacity. If you split Z into multiple latents, you dilute the signal and performance drops. Two features are sufficient and necessary.
Deep Dive 2, Attention-Free versus Attention-Based. When does each win? When your sequence length L is small and fixed, like Sudoku's 9x9 grid, token mixing MLPs beat self-attention. You can afford L's L mixing with fewer parameters, and the bias is perfect for local structure. For 30x30 grids in Maze and ArcAGI, self-attention's global receptive field and parameter sharing win out because the MLP token mixer becomes over-parameterized and under-regularized.
This is dataset shape alignment. Design the interaction pattern to match the spatial prior. Attention isn't universally superior, but on larger grids, the inductive bias plus soft global routing helps generalization under limited data, especially when augmentations are heavy but still imperfect.
There's also a learned sparsity angle. Attention can implicitly learn which tiles to connect across long distances, while fixed MLP mixers are dense and may overfit local motifs without the routing flexibility.
Deep Dive 3, Halting and Compute Economics.
HRM's ACT trained a Q-value pair for halt and continue, requiring an extra forward pass to estimate the counterfactual of continuing. TRM simplifies to a single halting head trained via BCE against correctness, which removes the second pass and empirically yields comparable or better generalization.
From a compute perspective, during training, you have per-step latency. During inference, you still run the full end supervision steps to maximize performance. Or you can enable early stopping to reduce tail latency. It gives you a control knob, more steps for accuracy, fewer for throughput.
One caveat: training halting on correctness creates a sharp boundary when ground truth is unambiguous. For tasks with multiple valid outputs, you'd want a softer notion of sufficiency or a learned confidence calibrated against a validator. Otherwise, you risk premature halts.
In production, we've seen teams set policy caps like stop if halting head is above 0.9 for 2 consecutive steps, which stabilizes variance and keeps the mean latency budget predictable.
Let's talk business cases. Who should actually care about TRM right now?
3 profiles jump out. First, manufacturers doing visual pattern reasoning on low-power inspection devices. Think grid-like layouts, subtle geometric rules, and scarce labeled data, where tiny models plus heavy augmentation deliver 20-30% defect detection improvements within 2 quarters. Second, logistics firms solving constrained pathfinding at the edge, where maze-like reasoning cuts exception handling times by double digits. Third, regulated industries needing on-prem reasoning for privacy, healthcare image triage or lab instrument QC, where frontier LLMs are impractical, and TRM's 7M parameter footprint slots into existing hardware.
I'll add a practical case. An e-commerce operations team used a TRM variant to autocorrect mispacked order patterns from scanner grids. With only 1K annotated error cases plus augmentations, they reduced repeat packing anomalies by roughly a quarter over 3 months because the system iteratively refined the proposed fix before committing.
And in telecom, we prototyped grid-form resource allocation for small cells. A TRM trained on 1 to 2K labeled layouts with dihedral and color remappings learned to propose and refine frequency plans, trimming interference violations by about 18% in offline A/B tests compared to a greedy baseline.
The unifying theme is small data with strong invariances. When augmentation can reflect plausible transformations, recursive refinement extracts more utility per label than a one-shot predictor or a prompt-engineered LLM.
Some executives listening will ask, why not just scale TTC with a large model and call it a day?
2 reasons: unit economics and control. TTC inflates inference bills and increases latency variance, and you're at the mercy of a vendor's roadmap. With TRM, you can bound compute, deploy on device, and keep IP and data governance in-house, which many boards now prioritize.
Also, TTC can amplify reasoning errors if your sampling strategy doesn't explore the right neighborhoods. TRM's inner loop explicitly repairs its own outputs, which is algorithmic, not stochastic, making failure modes more analyzable.
That said, there's a synthesis path. Use an LLM to generate or validate training data, design augmentations, or propose rule checks. Then let TRM carry the final deterministic solving at the edge.
Or fuse them at inference. An LLM suggests an initial Y, TRM refines it through recursion. When connectivity is available, you get a boost. When not, TRM still operates autonomously. Let's challenge an assumption. What's a non-obvious risk or bottleneck in TRM adoption?
Everyone obsesses over model architecture, but the real bottleneck is the correctness signal density. Deep supervision only works if each step's target fosters incremental improvement. Weak supervision or noisy validators collapse the gradient scaffold, and you get plateaus despite perfect code.
I agree, and I'll add a contrarian point. Too much recursion can overfit the improvement path rather than the task. We saw performance drop when cranking T and N beyond the sweet spot because the model memorizes stepwise rituals that don't transfer.
From ops, debugging recursive failures is like debugging a distributed system. Misspecify the update order or normalization and you chase non-reproducible flakiness. Invest early in stepwise telemetry, Y quality per step, Z drift, halting confidence histograms.
Strategically, the second-order effect is team structure. Recursion encourages instrumented iteration, so your ML team starts to look like a control systems group. You need new KPIs like effective depth at convergence, halt stability, and augmentation coverage, not just top-line accuracy.
On data scarcity, how far can augmentation carry you before the well runs dry?
If your invariances are robust, color permutations, dihedral transforms, translations, you can multiply data by orders of magnitude without leaking task answers. Beyond that, synthetic task generators help, but you need to ensure they sample the right concept space, not just pixel variations.
In a retail planogram setting, we used procedural generators to create shelf layouts with constraints, then validated with a rules engine. Combining that with TRM's deep supervision delivered a 22% improvement in placement error detection over the baseline CNN in 6 weeks.
Be careful with augmentation leakage. Never let augmentations put examples identical to test patterns. Segregate transformation seeds and audit for near duplicates at the grid and feature levels.
The theoretical caution is distribution shift. Augmentation teaches equivariances you encode. If the deployment environment violates those, say, skewed lighting patterns that mimic rotations, you can get confident wrong answers. Calibration and watchdog checks are essential.
Technical limitations. Where does TRM struggle today?
Memory scales with N when you backprop through a full recursion cycle. Push N too high and you OOM. Gradient checkpointing mitigates it but slows training. Also, the halting head tied to correctness is brittle when multiple valid outputs exist, so we need richer stop conditions.
On larger grids with long-range dependencies, the attention-free variant underperforms. You either bring back attention or add learned cross-patch routing, and you still don't get probabilistic outputs. TRM is supervised and deterministic by default.
Integration friction is real. If your stack is built around promptable LLMs, you need new serving patterns, stepwise execution, early stop policies, and telemetry hooks that product teams can reason about.
And for business leaders, model governance approvals may be smoother due to size, but you still have to document recursion behavior, halting logic, and failure playbooks. Auditors will ask how you control infinite loops and edge case oscillations.
Let's contrast TRM with deep equilibrium models for a moment.
DEQs explicitly solve for a fixed point and then differentiate through that equilibrium with implicit differentiation. TRM doesn't solve an equilibrium. It executes a fixed number of improvement steps and differentiates through the final block. In practice, TRM avoids the numerical fragility and solver tuning of DEQs at the cost of carrying more forward states.
That choice aligns learning with the actual inference loop. What you see is what you train, so you avoid the solver mismatch that can hurt DEQs when the forward solver differs between train and test.
And you skip line search headaches and Jacobian inverses. Always a win for production timelines. On architecture minimalism, why do 2 layers outperform 4 in small data regimes?
It's a bias variance trade-off under deep supervision. 2 layers plus many steps provide sufficient representational churn while minimizing parameters that could memorize. As the paper's ablations show, scaling layers up hurt generalization, while scaling steps held accuracy or improved it.
There's a cognitive analogy. Humans iteratively refine with a few mental operations rather than conjuring a deep tower of transformations. Recursion reuses a shallow operator, which is more sample efficient.
The lesson for practitioners is to scale steps before depth on small data, move compute from space to time.
And strategically, make everything as simple as possible, but not simpler applies. Simplicity wins when you need explainability, portability, and predictable costs.
Deployment playbook. How do you get TRM from paper to production? Start with a small, well-instrumented training loop. Implement the no-grad warm-up cycles and the final grad cycle faithfully. Add EMA, tune T and N for your memory budget. Enforce early stop gates in training to save compute. At inference, expose a knob for max steps and a halting threshold.
For data, codify augmentations as audited transforms with seed segregation. Measure augmentation coverage against real-world drift. Build a validator to sanity check outputs each step, like constraint satisfaction or rule checks, to catch hallucinated repairs.
Calibrate the halting head with temperature scaling or isotonic regression on a held-out set. Watch for overconfident halts after the first few steps, which can be tamed by requiring consecutive high-confidence signals.
On the org side, define KPIs beyond accuracy. Percentage of cases halted early without quality loss, average steps per task, and mean time to root cause a failure. These will decide your operational ROI.
Emerging markets perspective. What changes outside well-resourced cloud settings?
In regions with intermittent connectivity and tight power budgets, TRM's 7M parameter footprint is a game changer. On-device reasoning for agriculture mapping, microfactory inspection, or clinic triage becomes feasible without sending sensitive data across borders.
We've seen low-cost devices handle stepwise refinement within latency budgets when early stopping is enabled, cutting average steps by half without measurable quality loss on common patterns.
Edge compilation and quantization, in 8 or even 4-bit, play nicely with TRM because the same operator is reused every step, which simplifies kernel optimization and caching.
A third-order effect is resilience. Deterministic iterative solvers degrade gracefully. When the environment shifts, they don't explode into incoherence the way some sampling-heavy pipelines do. You get bounded failure behaviors.
Future directions. What's next for TRM-like systems?
Generative TRM. Decouple halting from strict correctness and learn to produce distributions over valid Ys. Think beam-like recursion where you refine multiple candidate solutions in parallel with shared Z updates.
Symbolic integration. Add a constraint layer between steps that clamps Y to feasible sets, like Sudoku rules or manufacturing tolerances, that turns the loop into a neuro-symbolic optimizer without heavy solvers.
Curriculum over steps. Teach the model to plan how many refinements a task needs based on features. Easy cases halt in 2, hard ones take 10. That maximizes throughput while preserving tail quality.
Theoretically, we need scaling laws for recursion, how accuracy scales with steps, parameters, and augmentation complexity. Once we can predict the knee, teams can budget compute scientifically.
From a business viewpoint, the competitive edge is owning the improvement process. Teams that learn to instrument, profile, and tune recursion will out-execute those who only swap models. This is an operational capability, not just a model choice.
Before we close, quick-fire heuristics for leaders deciding between LLM TTC and TRM.
If your task has strong invariances in small labeled sets, favor recursion recycles supervision efficiently.
If latency variance and cost predictability matter, prefer TRM with early stopping. If you need open-ended language generation, stick with LLMs and TTC.
If you can write down constraints, TRM shines. Turn them into checks between steps. Rules plus recursion beat prompts plus retries.
If fixed point math scares your team, good. TRM doesn't need it. Just ensure you measure stepwise residuals, not only final accuracy.
If governance and IP control are priorities, TRM's small footprint on-prem deployment will make your risk team smile.
Final thoughts, one line each.
TRM's power is humble. Shallow net, deep time, reason, refine, repeat.
Architect for steps, not size. Make the loop the product.
Simplicity scales across budgets and borders. Deploy where your customers are, not where your GPUs live.
Instrument everything. The path to the answer is your most valuable dataset.
Recursion is an algorithmic prior. Use it to turn few examples into durable competence.
That's a wrap. Less is more isn't just a slogan here. It's a systems and strategy doctrine. Thanks to our panel and thanks to you for listening to AI on AI. Until next time, keep your models small and your reasoning deep. Quick end-to-end wrap-up. Problem. LLMs with CO-T and TTC still fumble on structured puzzles and cost latency scales poorly. HRM's insight. Deep supervision plus recursion can emulate depth but leaned on fixed-point assumptions, dual networks, and double-passed ACT. TRM's key innovations. A single tiny two-layer network, two-state design, Y as current solution, Z as latent reasoning. Full recursion backprop on the final block, no IFT. Simplified halting via one-pass BCE. EMA for stability and architecture selection by grid size. MLP mixer for small L, attention for larger L. Results. Sudoku Extreme, 87.4%, Maze Hard AGI 5.1, 44.6378%, using 7M params, beating far larger models in this setting. Business highlights, small data regimes, edge deployment, predictable cost, governance-friendly footprints, risks and mitigations. Halting brittleness with multiple valid outputs, add validators and softer stop rules, memory pressure at large N, checkpointing tune TN, distribution shift despite heavy augmentation, calibrate and monitor stepwise. Future, generative TRM, neurosymbolic clamps between steps, curriculum over steps, and optional LLM hybrids for seeding or validation. Actionable playbook, scale steps before depth, instrument every step, choose token mixing by context length, enforce constraint checks, and treat recursion telemetry as first-class product data. Implementation cheat sheet. Pick T3 and N to fill memory headroom. Enable EMA. Choose attention if grids are 30-30, MLP mixer if 9-9. Add augmentation with strict seed segregation. Fit a validator, constraints or heuristics between steps. Calibrate the halting head and require consecutive high-confidence signals. Expose max steps and halt thresholds at inference. Add gradient checkpointing if N rises. For edge, quantize and cache kernels since the same operator repeats. Optionally fuse with an LLM for initial Y when online.
Strategic summary. Start where invariances are strong and labels are scarce. Inspection, planograms, resource layouts. Measure ROI via early halt rate without quality loss. Average steps per task, and defect or violation reductions. Document halting and recursion behavior for auditors. Deploy on device first to capture latency and governance wins, then scale with validator-assisted confidence.
Core insight to remember. Recursion is an algorithmic prior that turns tiny networks and little data into iterative competence. Reason, refine, repeat. Thanks for joining us on AI, and we'll see you next time where we keep models small, loops smart, and outcomes measurable. Share the episode with someone building in this space. The right idea at the right moment changes trajectory.